Hello class, so in this video we'll continue on section 5.3. As we saw in the previous video, we have a really nice way to evaluate definite integrals. And in the end, we saw how that was related to antiderivatives. Because if you want to evaluate the definite integral from a to b of little f, oh, and there should be a dx there. So always write dx, sorry about the dx. What is that equal to? Well, find any antiderivative of little f, which we usually denote by capital letters, right? So in this case, big F, and evaluate f at the endpoints, right? And subtract those values. It's as simple as that. Right? And I also mentioned we have this notation here for f of b minus f of a. We're going to be using this notation just to simplify the work a little bit, and you'll see how that simplifies things. Okay. So let's go over some examples. And again, now it's going to be very straightforward. So suppose we want to find or calculate the following definite intervals. We want to find the net area on the interval 0 to ln of 2 of e to the x dx. Well, with the fundamental theorem of calculus, if we want to do a problem like this, what do we want to do first? First, find an antiderivative for the whatever function we're integrating. So first, find an antiderivative for whatever function we're integrating. In this case, it's e to the x. Remember, an antiderivative is just any function whose derivative equals little f. So as we've seen before, big F equals e to the x works, right? And you can check, or you can check that f prime of big F is just the derivative of e to the x, which is e to the x. So e to the x is an antiderivative of itself. Okay? So now that we found an antiderivative for little f, what do we have to do? We just have to evaluate this function at the endpoints and subtract it. Okay? So by definition, by this fundamental theorem of calculus, what's the next step we're going to do? Well, this integral here, and notice the notation I'm going to use. It's going to be equal. Well, this function here, this antiderivative that we found, we're going to evaluate at the endpoints, right, and subtract them. So remember, this notation here means e to the b minus e to the a, right? Evaluating the antiderivative of b and subtracting at a when we evaluate the antiderivative of a. And this is the notation you're usually going to see. So I would always recommend writing this step, right? Always write this step here. Of course, in this case, the lower bound a is 0. The upper bound b is ln of 2. Okay. What does this equal? All this means is evaluate the antiderivatives at these values, right? So first evaluate at b minus the antiderivative evaluated at the lower endpoint, which is a, which is 0. What do we get? Well, what's e to the ln of 2? Remember, e and the natural log, exponential base e and the natural log are inverse functions. So remember, those things cancel out. So we're just left with 2. Now, anything to the 0 power is 1. So e to the 0 is 1. And this equals 1. As simple as that. Now, compare this to what we did in section 5.2 when we were trying to find the definite integral using the limit definition. See how much work that was. It was ridiculous, right? A lot of work. It was possible, but it was a lot of work. Now we have this really easy shortcut. Just find an antiderivative and evaluate at the endpoints. That's it. As simple as that. Okay. Now let's do this other example, part B. Now we're trying to find the definite integral on the interval. So what's the interval? We're doing 1 to 2. The definite integral from 1 to 2 of what is the function in this case? It's 2 over s minus 4 over s cubed ds. Remember that the whatever variable is after the d has to match the variable of your function, which in this case is s. Okay. So how do we do this? Well, it's going to be the same process, right? We can use the fundamental theorem of calculus. Now, notice one thing, and I'm going to show you an example of when the fundamental theorem of calculus doesn't work. Right? Remember, the assumption is that the function we're integrating is continuous on the interval. So notice in this case, e to the x is continuous everywhere, so that works. Now this function, 2 over s minus 4 over s cubed, well, that function is not continuous everywhere, right? Because if we plug in 0, it's undefined. So it's not continuous near 0, but on the interval 1 to 2, it is continuous. So in this case, it's fine to use the fundamental theorem of calculus, but you always have to check whether your function is continuous. Let me make a note of that. Always check if f is continuous, always. If it is not on whatever interval you're working on, then you can't do this trick. And I'll show you an example after this. Just a note, this function, f of s equals 2 over s minus 4 over s cubed is continuous on 0, 1. So we can use the fundamental theorem of calculus. That's the only condition you need. 1, 2, sorry. That's the only condition you need. Okay. So before we do this, we can use some of the properties of integrals. For example, here we have a difference. We know that we can separate the difference. It's just the same as the integral from 1 to 2 of 2 over s ds minus, and here I move the constant, the minus sign inside, of 1 to 2 of 4 over s cubed ds. And on this part, I can already move the constant out. Oh, actually, that looks kind of weird. Let me circle like this. Here, I already moved the constant out. And that's the next step I'm going to do to simplify. Whenever we have a constant multiplying the function, we can move it out, right? So in this first definite integral, we can take out the 2, right? That's multiplying 1 over s. And then here we can take out the 4. That's multiplying 1 over s cubed. Okay. Now, we're almost done. We're almost to a place where you can find an antiderivative. The only thing is, maybe you don't remember this property for finding antiderivatives, but for something like this, okay, so this one's a little bit tricky. So let me leave this one like this. This one I'm gonna rewrite as s to the negative 3. Remember, you can always do that trick. If you have an exponent on the bottom, you can move it to the numerator, and you just have to make the exponent negative. Okay. So let's work with this part first, because it's gonna be the easier part to work with. So let's go to another slide. So we have negative 4, integral from 1 to 2 of s to the negative 3 ds. Again, s to the negative 3 is continuous on this interval. By the fundamental theorem of calculus, you first find an antiderivative. So a big f of s such that f prime of s equals f of s, right? So an antiderivative of this function. We have a formula for finding f of s, big F of s. What was the formula? It was kind of like the opposite of where we're taking derivatives. You add 1 to the exponent, so negative 3 plus 1 is negative 2, and divide by that new exponent. And we're just going to move the negative in front, so we have s to the negative 2 divided by 2. Then we evaluate at the endpoints. Okay, so then the 2, the integral from 1 to 2 of s to the negative 3 ds, then is by definition this thing here. Remember the notation, evaluated at the endpoints, which just means plug in 2 and then subtract what you get when you plug in 1. So we plug in 2 minus, now you plug in 1. Remember there's a minus here, so you have to include it when you write this thing here, when you plug in 1. 1 to the negative 2, 2. What do we get here? So 2 to the negative 2, that's 2 to the 2 on the bottom, so that's 4 times 2 is 8. It's negative 1, 8. Minus minus is plus. 1 to the negative 2, and 1 to any power is 1. So it's going to be 1/2. If you get a common denominator, multiply 1/2 by 4 over 4. 4 minus 1, so you get negative 3/8. So what do we conclude? What is this thing here? Well, we found this part to be negative 3/8. Now we multiply that by negative 4, so we get 12/8, which is, because the negatives cancel out. Here we can simplify. You can divide both by 4, you get 3/2. So this whole part here, including the minus, which I remember I took over, this whole part here is 3/2. Now we also have to find what this is. So we need to find what 2 times the integral from 1 to 2, 1 over s ds is. Now remember, when I show you this trick here for finding antiderivatives of power functions, remember that the restriction was, because how can we write this? We can write this as 2 times the integral of 1 to 2 of s to the negative 1 ds. The condition was when your exponent is negative 1, you can't use this trick, right? So an antiderivative of this wouldn't be s to the 0, which is 1. Right? Because if you were to follow that rule, we would be saying, okay, add 1 to the exponent, divide by that. Oh, shoot, we're even dividing by 0. Okay, can't do that. So this rule doesn't work. It works for any exponent other than negative 1. So I have to think, okay, what function has derivative 1 over s? Well, we've actually already seen one, right? Maybe you remember, but what's a function whose derivative is 1 over s? Well, hopefully you remember. So let's do the same thing. Want a function f of s such that f prime of s equals 1 over s. Well, that's an antiderivative. Well, what function works? Well, I think the natural log works. And if you remember, what's the derivative of the natural log? It's 1 over s, right? You can check. F prime of s equals the derivative of ln of s, which we know is 1 over s. Of course, this derivative only works on the interval 0 to infinity, not including 0. It doesn't work for negative numbers. But here our interval is the interval 1, 2. So we're fine, right? If this interval were negative, we would have to be a little bit careful. I think you're going to see that in calculus 2, if I'm not mistaken. So for now, whenever the interval is positive and you have 1 over s as your function, ln of s is always a derivative. If the interval is negative, you have to be careful. You have to put an ln of the natural log. But for now, don't worry about that. So hopefully you believe me that ln of s is an antiderivative of 1 over s. So now we can finish integral from 1 to 2, 1 over s ds. By the fundamental theorem of calculus, 1 over s is continuous on this interval, right? So by the fundamental theorem of calculus, this is the antiderivative evaluated on the endpoints. And notice I'm always writing this step. Please always write this step. It's going to make everything easier for you and everything easier for the grader. Okay. What is that equal to? Well, just evaluate the natural log at the upper endpoint, upper boundary, minus the natural log at the lower boundary. ln of 1 is 0, so this is just ln of 2. Okay. Remember, we still have to multiply by 2, right? Because we left this 2 on the outside. So this whole thing is 2 ln of 2. So let's go back here. That part was 3/2. This was 2 ln of 2. So we combine all of that. We get that the net area bounded by this function on the interval 1 to 2 is 2 ln of 2 plus 3/2. Remember that this negative here was already taken into account when we found 3/2. And that's the answer. So even a really complicated function like 2 over s minus 4 over s cubed, imagine trying to do this with this definition using limits. Oh man, it would take forever. But here, it's easy. Of course, this one took a lot of work, right? Because we spread this out into two definite integrals. Right? So we simplified first, and we had to find each definite integral separately, right? But other than that, it wasn't really that bad. But when we separated into parts, both definite integrals were easy to find. Right? So once you find them, just put them back into this part here, and then you get your answer. Now, I said I was going to show you one problem with this method, or one thing you have to be careful. So let's say we want to do something like this. We want to find the definite integral from negative 1 to 1 of 1 over x dx. Remember, the first thing you want to do the only thing you have to worry about before applying this theorem, the fundamental theorem of calculus, is that this function has to be continuous on whatever interval you're working in this case, or let's say in this case, look at the function 1 over x. It's undefined at 0, so of course it's not continuous. Right? So what does this mean? Here we can't apply the fundamental theorem of calculus, which I'm just going to denote by FTC. So that's going to mean fundamental theorem of calculus. Which means here you can't just find an antiderivative and evaluate at the endpoints. You can't. Right? So here we don't have the tools yet to do something like this. It's possible to find what this is. In this case, we can't, unfortunately. So that's just the one thing to be careful with. That's like a sort of trick question that someone could ask you in an exam. They could give you this integral and ask, can we use the fundamental theorem of calculus? So what would you say? We can't, because f of x equals 1 over x is not continuous on the interval -1 to 1. So the fundamental theorem of calculus does not apply. Okay. So hopefully that shows you how to use the fundamental theorem of calculus, at least the second part, right, where it tells you how to evaluate definite integrals. This is a very powerful tool, of course, right? Because, for example, a lot of times you have some sort of function that's approximating something that you're interested in. And in that approximation, you really want to know what the net area is. Well, as long as your function is continuous, now you have, and you can find antiderivatives for it, now you have a really nice way to find what this area is. Just find an antiderivative and evaluate at the endpoint.